Hi, I'm Sebastian Romero from Arduino. In this session, I will demonstrate how to do predictive maintenance with Arduino and LoRaWAN. Arduino is both a company and an open electronics platform based on easy-to-use hardware and software. The project started in 2005 as a low-cost prototyping solution. Now with Arduino Pro, we bring all the knowledge and the experience that we gathered over the years to the professionals. The Arduino platform simplifies the development of hardware solutions from prototyping to manufacturing. It consists of thousands of libraries to support almost any sensor or actuator that you could think of. Also, there is a huge worldwide community that provides you with support and inspiration. Since this session is about predictive maintenance, we need to clarify what we mean by that. There is repair, which is a type of maintenance that happens too late. It means mending something that is already broken. Fixing it is usually very urgent for time-sensitive processes. If there is a fault in a system, first the staff has to notice it. Then they have to report it and wait for someone to fix it. This may cause delays and can potentially stop a whole business from operating. That's not good. Usually, when we talk about maintenance, we mean preventive measures to keep a machine functional for as long as possible. And this is failure prevention. Examples for maintenance can be cleaning, adjusting, or lubricating machinery, or even replacing parts. Now, there are two different types of maintenance: scheduled maintenance and predictive maintenance. Scheduled maintenance happens at predefined intervals, whether or not the maintenance would already be necessary. With such an interval, you may or may not catch the right moment to prevent a device from failing. The idea of predictive maintenance, on the other hand, is to predict the best moment to perform the maintenance based on historical or live data. Predictive maintenance describes techniques to analyze the condition of hardware and predict when maintenance should be performed before an inconvenient moment comes, before something breaks. It can be seen as a replacement for scheduled maintenance, which comes with a lot of benefits. It can help you to save cost on the repair of otherwise completely broken equipment. If you perform the maintenance before something breaks, you may only need a spare part. There can be a shorter outage or no outage at all. If you perform the maintenance before something breaks, there's not going to be any outage. You can have an optimized use of the maintenance staff because you will have a very good understanding of when exactly the maintenance staff has to show up. On top of that, you can also optimize the stocking of spare parts. Because you will know when exactly you're going to need spare parts, you can order them just in time. And predictive maintenance solutions are usually technology agnostic, which means that they are independent of the manufacturer of a device. And if you don't have to do any hardware modification, this means that there's not going to be any warranty issue. To implement a LoRa-based predictive maintenance solution, there are 4 steps involved. First, you need to choose the hardware you need for your solution. Second, you will have to make it smart so it detects what it needs to detect. Third, you will have to connect it to the cloud so the data is available anywhere. And 4, you will have to inspect the data and act upon it. First, you choose the hardware you need. At Arduino, we have different offerings when it comes to LoRa-based solutions. One of them is the MakerWAN 1310, which is a board from the Maker family. It comes with a 48 MHz microcontroller. It has a LoRa module, you can power it with a battery, and it has a secure element which allows you to do encrypted connections. Another option is the Portenta H7 in combination with the Vision Shield LoRa. Those products are from the Portenta family. The board comes with a microcontroller that has 2 cores which run at 480 and 240 MHz. It also has a Wi-Fi plus Bluetooth module. You can power the board with a battery, and the Vision Shield has a LoRa module on it. It has a low power camera that you can use for machine vision applications, and it has 2 microphones that you can use for directional sound detection and an SD card connector. And then there's the NiklaSense ME. It does not have onboard LoRa connectivity, but it's meant to be used as a sensor node, so you can connect it to one of the other boards. You can do so via Bluetooth or with a cable. It has a 6-axis IMU, it has a pressure sensor, it has a magnetometer, and it has a gas sensor. You can also power it with a battery. The second step is to make it smart. You can perform machine learning very easily these days on microcontrollers. This helps to augment the intelligence of billions of appliances. The benefits are that you can run machine learning on low-cost hardware, so you can easily embed solutions in everyday products. It can run on low power, which means it can work with a battery, which makes the whole thing portable. And the machine learning does not require internet connection. The data can stay on the device, which ensures privacy. There are different ways of leveraging machine learning for predictive maintenance use cases. One option is to use it with sound. So you would use machine learning to detect anomalies in sound. An example could be to detect the rattling sound of a broken dishwasher, or to detect the sound of broken glass in a factory. The accuracy is influenced by background noise, so this needs to be taken into account. Another option for predictive maintenance is to use machine vision. You can use machine vision to detect visual anomalies. An example could be to detect a broken light bulb or to detect a distorted saw blade. For machine vision, the accuracy is influenced by lighting. Yet another option for predictive maintenance could be to use gas sensing and machine learning. So you detect anomalies in gases. An example for that could be to detect wine that is going bad while aging in a barrel, or you could detect leaking gases in a factory. Another option for predictive maintenance is to use machine learning to detect anomalies in vibration patterns. And that's going to be the focus of the demo of this session. An example for that could be to detect if drill bits are wearing out, so you can use it to do a life expectancy estimation. Or you could detect a displaced washing machine drum, for example. The third step is to connect it to the cloud. I'm very happy to announce that we have recently launched the Things Network Arduino IoT Cloud integration. So now you can use a Maker WAN board to connect directly to IoT Cloud via a Things Network LoRa WAN backend. The configuration is completely automatic. In the background, it creates a Things Network application that communicates with the Arduino IoT Cloud. It just works out of the box. You may ask yourself why LoRa is a good choice for a connected predictive maintenance solution. And it's because LoRa is very resistant to noise, and it can cover a wide area, and there's even public infrastructure, so you could set it up anywhere you like. The wiring is very simple, because usually you would only need one gateway for many nodes, and it runs on low power. So again, you can use it with batteries or a solar panel, so you can install it anywhere you like outside. There's no network configuration needed, so you don't have to manage IP addresses and IP networks. And you can install it outdoors. So you could do predictive maintenance in the nature. The last step of implementing a remote predictive maintenance solution is to inspect the data. So once your nodes have reported that there might be something wrong with an installation or device, you will have to notice it and perform the maintenance. The Arduino solution for that is an IoT Cloud dashboard. So you can use it to visually inspect the hardware status of all your devices. You could read sensor data, and you can also track the sensor data over time. And you could even use it to send messages, for example, to alert the maintenance staff. Or you could also use it to trigger actions. So for example, if a machine is about to break, you can turn it off remotely. Let's have a look at the application example that we're going to use for the demo of this session. It's about detecting vibration anomalies. So we will predict mechanical failure through vibration patterns. So we're going to analyze those vibration patterns so that we can predict if a machine may fail in the near future. And that allows us to perform the maintenance before it actually fails. There are basically two different approaches to detect a vibration pattern. The rule-based approach would mean that we would analyze the data manually and then define a formula and an algorithm to detect an anomaly. Or we could go with a machine learning approach. If we were to simply calculate the intensity of a vibration or calculate a simple frequency, then we could go with a rule-based approach. But the problem really is that these vibration patterns are not always exactly the same, but we want to be able to detect them in the same way. Fortunately, machine learning can easily deal with these kind of variations. So for the demo, we're going to go with that. For our scenario, the end goal will be to have a visualization of the device status so we can see whether or not there is any vibration anomaly detected. We're going to use the Arduino IoT Cloud for it, and we're going to set up a dashboard. This allows us to track the device status and to inspect the failure history, and we could even extend it to intervene, which could mean that we could turn the device off if it's about to fail. Regarding the hardware setup, we're going to use a MakerBand 1310 that connects our predictive maintenance solution to the cloud, and a NiklaSense ME that acts as a smart sensor. The two boards are connected via SLOF cable so they can communicate with each other. The NiklaSense is mounted on top of a PC fan, so in this demo we're going to measure the vibration of the fan, which may indicate that it's about to fail. In place of the fan, you could imagine any kind of machine that could show vibration anomalies if it's about to fail. Here you can see the actual setup. The NiklaSense is mounted on top of a PC fan. What I'm going to do in the demo is that I will put my finger on the fan so that it slightly touches the blades. That will cause some vibration, which is meant to simulate mechanical wear. This is just a simulation. In a real-world scenario, it could be that, for example, the bearing of the fan is broken and would need to be replaced. Here you can see a schematic view of the training process. So first, we will have to train a machine learning model to understand what constitutes a vibration. So on the PC, we're going to use the Arduino IDE to upload a training sketch to the NiklaSense ME. This sketch does nothing else than accessing the accelerometer value and turn it into a simple number. That number is then being forwarded by the Edge Impulse data forwarder to the web app, which is called Edge Impulse Studio. And in Edge Impulse Studio, we then take that data and do a spectral analysis. So we will have a look at the frequencies of these vibration patterns and extract those features from it. Once we have that, we can then perform a training step, which turns these features into a machine learning model. And when that is done, we can download the machine learning model as a sketch. In the previous step, we acquired a machine learning model as a sketch. And now that we have that, we can use again the Arduino IDE to upload that machine learning sketch to the Niklas Sense ME. At that point, the Niklas Sense is going to be capable of detecting vibration anomalies. In order to connect the predictive maintenance solution to the cloud, we will have to upload an IoT Cloud sketch to the host board, the MakerVan 1310. Once the software is deployed, the detection process can run. The Niklas Sense constantly reads from the accelerometer and runs a classification to see if there is a vibration or if it's running normal. Whenever the MakerVan requests the current state of the vibration, it will send that data over the cable. The MakerVan reads that data, and whenever there's a change, so when it changes from running normal to vibrating or vice versa, it's going to upload that change to the cloud. And in the cloud, there's a dashboard in which we can see the status of that variable. Back to the training process in Edge Impulse Studio. In order to create a machine learning model, we have to go through a couple of steps. So first we have to gather the raw accelerometer data, and we then have to process that data and filter it. Then we have to extract the unique features, which is in our case the unique properties of a vibration. And then we have to train the machine learning model. Step number 1, gather raw data. We're going to use the Niklas Sense's onboard accelerometer to gather vibration data. This is delivered with 3 different values which correspond to the 3 different axes. If you have a machine that actually vibrates in different directions, then you may want to use all the 3 different axes. In that case, the way you mount your sensor matters, so the orientation matters. For our demo, we're going to do a little simplification, which is that we're not going to look at the direction of the vibration, but just at the frequencies and the magnitude. So we're going to calculate the magnitude of the motion vector by squaring the XYZ values, summing them up, and then calculating the square root. On the right-hand side, you see a preview of the serial plotter, which is a feature of the Arduino IDE that shows you how this value fluctuates as soon as the vibration starts. What we will have to do in the Edge Impulse Studio is to gather that raw data and label it. If, for example, the device that the sensor is attached to is running smoothly, then we have to label it accordingly. If the device starts to vibrate, we have to classify that data as a vibration. Step number 2, process data. One important aspect when looking at vibration patterns or data that is delivered from the accelerometer sensor is the window size. And the window size defines how many milliseconds of sensor data should be considered for a classification at a time. Because this is continuous data that we get from the sensor, so you have to define how much of that data do we want to have a look at for the classification. And the size of that window really depends on the vibration pattern. So if you have a complex vibration that maybe takes a bit of time to execute, you may need a larger window size. But if you have just a constant vibration, a small window size is probably enough. In Edge Impulse Studio, when it processes the data, it turns the data from the accelerometer into a frequency domain. So you can see at which of the available frequencies in the data there is the highest amplitude, so the highest amount of motion. And for each sensor you will get certain frequencies which are just not relevant to the motion that you're trying to analyze. And the goal is to filter those frequencies out. Within the remaining frequency range, it will try to find the peaks, and those peaks are the unique characteristics of the vibration that you're trying to detect. Step number 3, extract features. Once you have pre-processed the data, you can then generate the features, and it will extract the unique characteristics of your input data along with the classes with which you labeled that input data. In our case, we have normal and vibrating. So you see in this visualization of the features that there are certain characteristics which constitute the data of a vibration. So there's obviously higher amplitudes of motion if it's vibrating, and they tend to happen at specific frequencies depending on the vibration pattern. You can also use that visualization to find bad training data. So if there's overlap in the different classes, it can be that it's just very similar, or it can be that the training data is not so well recorded and you may want to get rid of that sample. Step number 4, train the machine learning model. Once you have those features extracted, you can train a model that is able to take a look at some input data and then tell you which class it thinks that it belongs to. In our case, we have 2 classes, which is normal and vibrating. The model learns based on the provided vibration samples. You may have to adjust the default learning cycles as needed. So for some input data, it may take a couple more cycles for the model to learn properly how to distinguish. Watch out for overfitting, which means that if you have a very high accuracy of almost 100%, it could mean that your machine learning model is a bit too much geared towards your input data. What you want in general is a machine learning model that can deal with data that it hasn't seen. So data that does not come from the training data. Now that we have learned how the training and the classification process work, let's have a look at the actual example and run through it together. The first thing that we need to do is to upload the training sketch to the NICLA Sense, which measures the vibration. In this sketch, we basically access the values from the accelerometer, and we read these values 100 times per second, so a frequency of 100 Hertz. And that returns me 3 different values for the 3 different axes. But in order to simplify the whole thing, we would like to have just one number, so just one motion vector. And to achieve that, we just take the squares of these values, we sum them up, and then we calculate the square root. And that gives us the magnitude of that motion vector. So this is a single number that we then print to the serial port. If you upload that sketch to the Niklas Sense and you open the serial port, you see that it spits out numbers. And if I tap on the board now, you'd see that these numbers start to fluctuate. There's another tool which allows you to see that even better, which is the serial plotter. And in that one, as soon as it's calibrated, you will see that the value, it fluctuates a little bit. There's a little bit of jitter in it. And if I now tap on the board, then you will see that you can clearly distinguish what constitutes a vibration. Now, in that case, I'm just tapping on it. And this is what we're going to feed into the machine learning model. So it's going to learn what constitutes vibration. Now that the Niklas Sense is ready to forward that data from the accelerometer, we can open the Edge Impulse Studio, which is what we're using to create the machine learning model. So the first thing that we need to do here is to feed it the data from the Niklas Sense. And to do so, there's a tool provided by Edge Impulse called the data forwarder. So I'm going to start it with a frequency of 100. I choose the board and it connects to my project. Now we have to record samples for 2 different labels. So the first one would be the normal state, which is in our case the fan which runs smoothly. And the second one would be the fan which has some sort of mechanical failure. So it's going to have vibration. Let's start with normal and let me start the fan. Now that it's running, I can click start sampling. So now during 10 seconds, it's going to record the data from the sensor. Okay. Now that we have that, we need to do the same, but now with vibration. So to do so, I put my finger slightly on the fan to create vibration, and I'm going to start the sampling. Okay. Now you can see that those 2 graphs, they show quite different numbers. So to create a robust machine learning model, you would need to train it with many of these samples, and I already prepared that for us. So once you have collected enough data, you can move on to extract the features of that data. I click here on Spectral Features, which is what we set up for this impulse. And in that step, basically we extract the frequency of these vibrations, and there's a couple of parameters that you can tweak. I found that having a look at the vibration frequencies between 0 and 30 Hertz is well suited for our use case. So I set the cutoff frequency to 30, which means it's going to neglect all the frequencies above 30 Hertz. So it's going to have only a look at the peaks within that frequency range here. And when you generate the features from that, what you get is a visualization that shows you visually how these 2 different labels are represented in terms of their characteristics. So you can see here the blue ones, which they represent the normal state. So here you can see the different frequencies and almost no peaks, like very little amplitude in it. Whereas the vibrations, they are like in the upper part of this cube, meaning that there was more movement in those vibrations at these frequencies. And you can also see that it's pretty nicely separated. So there's very little overlap in which it would be uncertain whether it's in the resting state or in the vibration state, which is very nice, because that's going to help us to generate a robust model. So now that we're also happy with that, we can move on to the actual training. And I left it pretty much at the default parameters, except of the number of training cycles. So I let it train for a little longer. So I bumped this number to 100. And then I clicked start training. And what you get is a performance analysis. So in that case, it performed with a 93% accuracy, which is pretty good. You don't want to achieve 100 or something like that, because that likely means it's overfitted. So that means it would be too well adjusted to exactly the training data, but you want to have some sort of variation that it can deal with. So 93 is pretty good, and since we're also happy with that result, all that's left to do is to deploy the model. We could also perform a model testing, which gives you a better understanding of how well the model performs. For that, you need to provide extra testing data, which the model hasn't seen yet. At this point, we're not going to do that, but we're going to just deploy our model as a Arduino library. So you click build, and it will generate the package for you that then can be installed on the board. The package that we downloaded contains the machine learning model. That one needs to be copied into the Arduino libraries folder. I edited one of the example sketches that comes with that package for the classification, and I only slightly tweaked it. So the only thing that I added is that whenever it does a prediction or a classification, if the current prediction is vibrating, then it will turn on the red LED. If it's normal or uncertain, it will turn on the green LED. Now, if we open the serial monitor and if we turn on the fan, we can see a preview of the classification. So now it's pretty sure that it's everything is running normal. As soon as I touch the fan with my finger, it starts to pick up that vibration, and eventually it's going to classify it as a vibration. So something is going wrong, which is currently my finger being on the fan. As soon as I lift my finger, it's going to go back to normal. The other thing that I added to the sketch is that it can work with a host board. So we're going to use the maker van board to read that value from the Nikola sense. And whenever it requests the current class, the current prediction, it would just send a 1 if it's currently vibrating, or a 0 if everything's going well. And it would write that over I²C. So all that's now left to do is to hook it up with the host board and send the data to the cloud. Now that the classification is working, we can hook up the Nikola Sense with the MakerVan 1310 host board and connect it to the cloud. To do so, I open the Arduino IoT Cloud web app. Here you can see all my registered devices. The one that we're currently using for this demo is the MakerVan 1310. If this is the first time that you set it up, you click on Add Device, Arduino, and wait for it to be registered. While the device is being configured, it automatically creates a Things Network account and integrates that with the IoT Cloud account. All of that happens automatically and works out of the box. The next thing that we need is a thing, which is like a project. And the one that I prepared is called Predictive Maintenance. And each of the things can have multiple variables. And the interesting one for this demo is the one that I called running normal. So whenever the fan is running normal, this variable should be set to true. Whenever it detects a failure, it should be set to false. And everything comes with a IoT Cloud sketch that can be uploaded to the board. So let's have a quick look at the one that I slightly adjusted for this demo. So it's pretty straightforward. What happens in this sketch is that it first connects to the cloud when the board starts. And then while it runs, every couple of seconds, it asks the Niklas Sense for the latest status. So it asks the board whether it detects a vibration or if it's running normal. And whenever it detects a change in the state, it would set the cloud variable to that value. So if it's not running normal, it would set that variable to false, and this is automatically uploaded to the cloud. If we upload this sketch to the board and open the serial monitor, we see that it starts to connect to the cloud. In order to have a nicer visualization of this variable, we can use the dashboards. I also created an example for this demo, which is again called Predictive Maintenance. And here I have prepared two widgets. And these widgets reflect the running normal variable. So whenever the device detects a vibration, it will set the variable to false, and this widget here should turn red. And on the right-hand side, you see a chart widget, which allows you to keep track of the changes of that variable. So you can see how the device status changed over time. So let's try it out. I'm going to put my finger onto the fan to create a vibration. And then within a couple of seconds, we should see that reflected here. So it should now send the updated state to the cloud, and you can see that it now turned red. And if we switch to the live tab here, you can pretty much see whenever this turns back to normal. So let's wait a couple more seconds until it turns green again, now that I lifted my finger from the fan. And it worked. That's the end of the demo. We had a look at the whole process of training a machine learning model, deploying it to a sensor node, and then hooking it up with a LoRaWAN capable board, connecting it to the cloud, and eventually visualizing the result of the classification. Thank you so much for listening. I hope you enjoyed the session.